Okay, going to finish off lecture 5 today. So, for a lot of simple molecules, we think of a chemical formula applying to one molecule. And that's the case for a lot of things, like NH3 or CH4, where you give the chemical formula and there's only one way to draw that molecule. But, particularly with organic chemistry, the same formula can sometimes give rise to 10, 20, 40, 100, 1,000, a million different structures made out of the same atoms. So we call those isomers. So isomers have the same chemical formula. They're made of the same atoms, but they have different structures. And we can break them into two categories. The first are what we call constitutional isomers. So these have the atoms connected in a different order. So they would have different Lewis structures. These are also sometimes called structural isomers. And then we have the even more mind-blowing stereoisomers, where the atoms are actually bonded in the same order. But arranged differently in space. So stereoisomers actually have the same Lewis structure, but then where the atoms are actually placed when you look at the shape is different. And so first we'll look at constitutional isomers, then I'll show you one example of stereoisomers, but there are others that we won't get to. So, for example, if I have the formula C4H10, I have 4 carbon atoms, I have 10 hydrogen atoms. Turns out there's 2 different molecules I can make from this. Take a moment, see if you can draw 2 different molecules that have the formula C4H10. Okay, I saw a few people come up with the structures. The simplest one would be to put your 4 carbons in a row and then just fill in the hydrogens around them. And then the other thing I could do is put 1 carbon in the middle with 3 carbons around it. Of course, those structures are kind of a pain to draw, so probably I would prefer to draw them as skeletal. So 1, 2, 3, 4, that would be one of them, and then the other one would just look like that as a skeletal structure. So those are definitely different molecules. They're made of the same atoms, but they're going to behave differently. They'll have different properties. All right, how about the formula C3H6? All right, so one way to do this would be to have a double bond between two carbons, and then a single bond with the other one. So like that. The other one requires a little trick. I saw some people trying to use this trick on the first one, but it doesn't work on the first one. You could make a ring. So you could make 3 carbons in a triangle, each with 2 hydrogens. So again, those would be simpler skeletal structures. So the idea is you can take the same atoms, make different molecules. And then the last one I would talk about would be stereoisomers. And you might be thinking, well, how can I have 2 atoms that are bonded the same way but are arranged differently and become different molecules? And the simplest way to do it is to have what we call cis-trans isomers. Okay, when you make a double bond between 2 atoms, the other atoms bonded to those carbons, so here if I were to draw this out, this one would have a hydrogen here, a CH3 here, hydrogen there, CH3 there. When you have when you have 2 double bonded atoms, it fixes everything in place so that those atoms can't rotate around. In lecture 6, I'll actually explain why that's the case. But because it locks those things in place, these 2 things here, which both have the formula C4H8, right? If I draw in the carbons here and here, you can see these both are C4H8. And in each one, they're bonded in exactly the same order. We have a CH3 group bonded to a carbon. That's double bonded to another carbon. That's then bonded to another CH3 group. So the order is exactly the same, but they're arranged differently in space. I built models of the 2. For those of you watching at home, you can just grab them in the classroom sometime. I'll pass them around the room. And it turns out they are different molecules that have different properties. So where the 2 things are on the same side, we call it cis. Where they're on opposite sides, we call it trans. Where this is relevant to you would be with things that you eat. Trans fats. So it turns out that naturally occurring fatty acids, when they have double bonds in them, they have the cis configuration. When you do this thing called partial hydrogenation to them, it flips some of those double bonds so that they have the trans configuration. That actually changes the way they behave. It gives them a longer shelf life, but it also turns out, we just recently realized, oh, it makes them actually really, really bad for us. For years, actually, people were told, oh, you should eat margarine instead of butter, because margarine isn't made from animal fat, and so it's healthier. And then more recently it became, oh wait, margarine is full of trans fat. So remember that thing we told you? Sorry. Ralph. So the question is, if I had a big vat of fat, could it be made of lots of different kinds of molecules? And the answer is yes. So it could be made of different isomers of the same formula, but it could also be made of, different chemical formulas. Um, so speaking of fatty acids, I want to go back. Actually, this is a slide that Mr. Bennett didn't get to, so we're going to just finish this one off. Fatty acids are these long chain molecules that have a carboxylic acid at the end. So this is back a couple pages. So on page 11. Now, first of all, I want to point out how cumbersome this drawing is that's up here. So let's start by just putting it in a much more pleasant form. How could I draw this in a more pleasant form? Skeletal structure, so 1, 2, 3. Okay, so there's my fatty acid. And the reason this molecule is on this slide is to bring up the point that when we talk about polarity of molecules, sometimes molecules can have two different personalities. And fatty acids are an example of that. Because this end that's made of all carbon and hydrogen is almost completely non-polar. But the end where the carboxylic acid is, this is polar. You've got partial positive on the carbon and the hydrogen. You've got partial negative on the oxygens. And so when you have big molecules, a lot of times they have parts that are polar and parts that are nonpolar. It doesn't have to be a term that applies to a molecule as a whole. So fatty acids, one thing we can use them for, we can make this end even more polar if we pull the hydrogen off, and then it has a negative, leaves behind a negative charge. So we use these as soap. You pull the hydrogen off, leave a negative charge, and you have the polar end and the nonpolar tail. In biology, these kinds of molecules are really important too. But we just want to point out that this polarity idea is not as simple as just pointing to a molecule and saying, that's polar, that's a polar molecule, that's a nonpolar molecule. Sometimes one molecule, if it's big, can have multiple personalities going on. All right. Have a great day.